audience. Hi, welcome again. This first talk will be essentially about methods and ideas that some we've explored, some we haven't explored. So this will be a fairly simple talk. And then João will follow and will give us the numbers, and we'll basically tell you what we've did in the past in the hope to control Caulerpa here in Fayal Island. Are we good? Okay. So, as you are aware by now, Caulerpa and other invasive species are a problem worldwide. The extent and the amount of effort that has been put to and the methods used worldwide have differed depending on the amount of resources available, on the ecosystem, on the habitat characteristics, and other variables. So there's basically different solutions. Different solutions have been pursued in different areas, and some are common and some are actually quite different. Ranging from, like Alexander has said previously, from hand picking, and this is a picture from Portugal, hand picking the Caulerpa using some sort of tool and then bagging it and then taking it into land. The use of copper impregnated tarps that are placed over the Caulerpa beds and left for a few hours, and then basically the way this solution works is the copper ions block basically, in a very simple terms, they block the ability of Caulerpa to make photosynthesis, and then it will basically die shortage of energy. Alexander has already talked about this method too. This looks like a very bright idea, very clever idea. Nevertheless, it has problems, it has issues with the application. Like Alexander said, you need really flat bottoms, and that's something that's not very abundant around here. In our case, it's not very useful. And logistically, you need a boat or some sort of raft or whatever to carry power that will, and cables and lines. So it's logistically, it seems like, I've never done it, but it seems like a nightmare logistically. And then the Australians, Australia is big. They like to do things, big time. So they're using salt and lots of it. They're using like 1,000 tons of salt to cover 4 hectares of Caulerpa infestation. That's a lot of salt. Logistically, it looks like a nightmare as well, and it's probably very expensive to do it. And again, you need flat bottoms you need flat habitat to do this. You can't do this over rocky, high relief terrain, because you need 10 times more salt just to cover what's on top of the rocks with high relief, or even more than that. So not a good solution for habitats like we have here in the Azores. And then in the U.S., by now everyone is familiar with this. The first and unfortunately, the only case of success, eradication success. They also used the combination of methods they used, and I won't go into this because Susan will talk about this in the afternoon. But you basically used chlorine, basically build these big traps and put chlorine in there, and it would basically chlorinate the algae, and use also. I'm not actually absolutely sure if to use copper. I don't think so. Just chlorine. Yeah. And then this is actually a picture from Hawaii, but like Alexander also mentioned, many people have tried the sucker, the super sucker in this case, but it's a different application. But the idea is the same. They remove algae that smother the coral reefs, and this way they try to keep the corals healthy and keep the algae, the macroalgae away from the corals. And basically they suck the whole thing. Logistically, also a nightmare, because you need a boat, you need big power supply, and you need people to then to remove the organisms that are sucked with the algae, and you don't want to kill everything that's sucked into the super sucker, right? Dry ice. This was used in California, I think, as well, and has also been trying in other places of the world. So basically, explore the lethal effects of temperature, on the high end and the low end. And of course, very simple principle: just cover everything and let it die off, because there's no sunlight getting there. Okay, so this brings us to the Azores case study, basically. And as you can, as you're probably familiar with, I'm sure you probably looked at, you've seen a chart of the Azores bottom around the islands, and you can guess that it's pretty dynamic, high relief walls and very hydrodynamic. So some of the things the ideas that have been put forward by other people and have been tried in other places, we also try to explore them and adapt them to our reality, to our system. And so this started in 2007. There was the program began in 2007, with the goal of studying the biology, but also looking at the methods that could be used, or selecting methods and testing methods that could be used in a large scale on a eradication and control program. And so this basically the methods that were tested, selected for testing initially, were the copper sulfide tarps that cover the Caulerpa, and actually, this is one of the methods, and we had to build I wasn't involved at this time, but the people that were involved, there's a lot of hard work building this, because this tarps from scratch. You go to the local hardware store, and then you buy materials, and then you start to build them, because we had a budget from a quote from the company that sells the French company that sells the tarps, and if I remember correctly, it was something like 50,000 euros for 100 tarps or something like that, and I wasn't sure if they could be reused. So it was really expensive. We couldn't buy them, so we had to come up with our own. So we had to build them. The problem with these tarps is that you have to building them. Once you build them, then if you can reuse it, that's fine. But then every time you go in the water, you have to clean them, you have to wash them with fresh water, you have to dry them, then you have to make a solution of copper sulfide, then you have to add some acid to stabilize it, then you have to pulverize it, then you have to let it dry. And people familiar with the climate, and if you've been here for a while, and you can see this process of drying and cleaning during the winter time in large quantities being a big pain, Okay, then the other issue is you obviously need to bag these tarps, because if you just throw them in the water, by the time you get to the Caulerpa, they'll be clean. All the copper will be washed out. And so this presents another big problem, which is there's air inside these bags, and it's very difficult to take all the air out. So, and if you're diving and you're taking a bag with air, and it's really, if you take a couple of bags, it's really difficult to work with this and go down without taking just too much extra weight. And so this is logistically, this was also a problem, and would limit your carrying capacity, basically. And so anyways, we tested it. Some tarps looked funny, but they did their job. A big problem was that, because you take the bags out and you open the tarp, and then you start placing it, and immediately when you take out the bags, you immediately start to wash out the copper, and then basically this creates a big cloud of copper, and sometimes you just can't see the diver, and copper is not the best thing to dive around every day for extended periods, but although they looked funny, they apparently it worked. So at least experimentally, it sounded like it could be a good method to be adopted here. Okay, the second method that was tested was not a super sucker, but it was a decent sucker. But the problem with this sucker is you need two divers. You need one because of the rhizoids that they creep to the rocks, and it's really difficult to get. You would probably need like a supersonic sucker just to take everything out. And so with a normal, a decent sized sucker, you need an additional diver scraping the rocks. It's very, very hard work. Okay, so there were issues. Like I said before, this method is very labor intensive. The method that was available then is very, very labor intensive. You need to clean, to rinse, to dry, to pulverize, to make the mixture, then pulverize, then dry it again, then bag it. So the divers cannot take many tarps, cannot use many tarps at the same time because they won't be able to push them down. And the tarp size is limited because you can't make a 5 square meter tarp and put it in the bag because you need 4 divers just to take it down, and huge bags, and not to mention the amount of waste that's being produced, because the bags all the bags used in one dive are going to be trashed typically, because you're going to have to rip them open to take the tarps out. And the other issue, of course, is the long-term exposure to copper sulfide, which is probably not very good for you. And then, but the problem is these methods were used and were tested and developed in areas that were mostly flat and fairly calm. And here, we don't have anything like that. Typically we have big swells, even in the summertime, even though we don't see waves like this, but there's a lot of hydrodynamic underwater. And if you can't really fixate your tarps on the rocks, they're gonna get lost, and it happened often. The other problem is we have walls. We have Caulerpa creeping up walls, so it's a vertical surface. It's very difficult to attach the tarps there too. So we needed to come up with a solution for this. And the same thing applied to, typically relief. There's a lot of relief, and Caulerpa grows in areas that are very dynamic, very high in relief. So how can we attach these tarps? That's a big problem, big issue. And then the other issue with the sucker, in my opinion, and Alexander has also mentioned that, and I totally agree with him. I don't like this method at all, because I think we're actually making things worse, because we're just fragmenting, we're just creating millions of fragments of Caulerpa. And even if we try to apply some sort of filter, on the boat, just because you're sucking, tons of water in the end of the day. So what are you going to do with that? You're going to put it in a tank, so you need a tank ship next to you, or you're going to pump it on land, but then you can only work close to land. You're going to put a sieve, but the sieve is going to collapse eventually, because fragments can be very, very tiny, and all the stuff that you're going to be sieving it through is going to just clog the sieves, and it's logistically, and in terms of potentiating further dispersal, I don't like this. And so we decided not to use this. So we had to develop new methods of using this copper sulfide tarps, which basically will solve the problem of attaching by building like bigger tarps. We put holes around the tarps, and then we created these elastics that you can actually adjust in length and have hooks in the ends. So you can create like a web of elastics, and you can adjust to different lengths depending on where you want to fixate it. And then using this, and then you can actually combine different sizes of tarps, and as many tarps as you want depending on the size of the area. And I think the most interesting innovation, I'll show you the video. I think it's more, I'll try to show you. Okay. So I think this is one of the most interesting innovations is we no longer use impregnation in land. We take the copper in a solid form in micrograins, and we put them in those charges. We call it charges. We put them in those vials basically, which allows us to, as you can see here, the application. First we put the tarp, we adjust it, we don't have to worry about the copper being washed away. I'll just run it again. Then we prepare the time of preparation in land is much shorter, because basically what you have to do is just fill these containers with the copper, and then basically they have these holes and have these rubber bands around. And after you put the tarp and you can adjust it, you don't have to worry about being, swimming in copper. And then when you're done, you just leave a little bit of opening, and then you put these containers, the copper containers, you just open, you remove the seals, and then you put it under, and then it just releases the copper slowly. And then you can move away, and then you don't really have to be in contact with water-saturated copper. I think this was a very interesting innovation, and the main advantages of these transformations that we did, the method already existed in principle, so we just adapted it to our needs. I think this is very important because we've greatly reduced diver exposure to copper in comparison with the previous form. We've increased carrying capacity by a lot. We can actually, before we could, one diver could place about maximum 3 square meters of tarp, and with this method, because we don't have to carry bags, and we don't even have to carry the tarps from the station to the boat and to the bottom, we can actually reuse the same tarps from here. We can just pick them from here on the dive and put them on the next colony. And so basically we can increase our productivity from 3 square meters per diver to experienced diver can do 20 square meters in one dive. And the preparation time is incredibly shorter than all the problems with weather being good enough to dry and wash and re-dry and impregnate the tarps. That's been reduced. It can adapt to the terrain. You can also adapt to the colony size, because we had tarps that range from 1 square meters to, we even had one, and different sizes. We even tested one, it was experimental, it was 20 meters by 4 meters wide. It was a massive, huge tarp. It's very difficult to use, so we didn't use it very often. It's much more resistant to swell than the previous methods. And we also need less copper, because less copper is washed when you open the bags. So we did some experiments, and we managed, initially we started doing this with basically the same amount of copper that we needed to impregnate, let's say 1 square meter, and we did basically a linear relationship, and we put the same amount of copper in the charge to put in 1 square meter tarp. But then we did some experiments and realized that we could use even less copper and be as efficient. And now we can do 2 missions in one day, because we also realized that, and we tested this, and we realized that we don't need to leave the tarps from one day to the next. We can put it in the morning, and then 4 hours later we can come back and move it to the next colony, and it will be as effective as a 24-hour. So less risk and lower cost for a square meter of treated area. The second method that we developed was inspired by, obviously, the method used in the US. But like I said, our system is very different, very dynamic, very high relief. We couldn't possibly use the big structures they used and then pump chlorine in there, because it would never work here. It was just, everything would just be wrecked after the first or second day. So basically what we did and we thought about was, sometimes we had small colonies that we wanted to treat, but we didn't want to put, big tarps. It would be like using a bulldozer to do something that you can do with a shovel. So we thought about something that would be more precise, something that would be more directed. And inspired by the idea of using chlorine, we developed these crazy machines for which we still don't have a name. But basically, this is all stuff that you get. It's very low cost. It's all stuff that you get from your local hardware store. You need a very small dive tank. This is something that this is a regulator that's used in domestic gas installations. This is an old dive rag. This is something that amateurs use in your garden just to pulverize your weeds or your vegetables or whatever, and then these some ballast, and basically you get this pumping machine that allows you to spray you put it very close, and I'll show you the video. It's, again, if it collaborates. Okay. And we use solid chlorine as well. We have these containers. We put this, this is swimming pool chlorine. Solid chlorine, you dump it in there, then you close it, and then the seawater will mix with the chlorine and start to dissolve, and then you'll get this concentrate, this chlorine mixture with salt water, and then you just apply it on, very specific, and then you'll immediately see the Caulerpa going white, and then it's dead. The only the big problem with this method is that you can only kill what you see. So if you have small patches or small branches that are growing in the canopy of the native algae, I mean, if you don't see it, you don't kill it. It's very localized. The tarp is more, if you see a colony, maybe you have some small patches that you can see around it, but if you do it by excess, and so you potentially kill everything that's around within that square of tarp. And so we tested the efficiency of both methods, and this is the control. This is just an example of some of the quadrats, the replicas we did. This is the copper, and this is the chlorine quadrats. And as you can see, you get immediate death of Caulerpa when you use chlorine, and then it takes a little bit longer for, this is time, it takes a little bit longer for the copper to go into action. But basically, a long time, the outcome is basically the same. You kill all the Caulerpa inside the quadrats, and then you start to see some regrowth of other stuff. And then, as you'll notice, at some point it's not absolutely zero, because you get some growth, but from creeping Caulerpa that's coming from the outside, because basically this was a quadrat in the middle of a colony. So this is when you don't have 0% doesn't necessarily mean that it didn't kill everything. It means that it's growing back into that quadrat. And so I'm just gonna now stream to some crazy ideas. Some might be just completely crazy, some might be useful. I don't know, we've tested some others we just discussed about it over Peters or whatever. Temperature, thermal stress has been tried. It's been tried with dry ice. It's been tried with warm water. We wanted to see if the high end of the thermal stress also could be used for Caulerpa waviana. We did a very simple experiment. Basically, you put rocks, 2 boxes with rocks of Caulerpa waviana, and one we poured. We bring them both right next to the surface, right under the surface. One we poured water at 60 degrees, and the other one we didn't. And then after a week, one was absolutely free of Caulerpa and everything else, and the other one still had the Caulerpa. So, but we started contacts with some companies, some private companies that work in the energy field, and some engineers to try to come up with a solution that would be economic, that would be feasible, and we didn't have much success. At first, people were kind of enthusiastic about the idea, but then, as you start to think about things like how much heat you lose when you boil water in the surface and you have to take it down during this trip, things about pumping salt water and having salt water running through heating systems. It just corrodes everything, it just kills everything, and no one really wants to do anything with salt water, the engineers that deal with this. So we just tested the principle. I mean, we know it works. If we can get a efficient way and cheap way to do it, then it could be part of the solution. We tested other more extreme methods. We took advantage of the building of the new harbor, and it had to be a huge amount of sand had to be removed from that area. And so basically, in areas that were more flat and they were fairly extensive and were right on next to the dock, so basically in habitats that were already transformed, they were already changed by man, we decided, okay, let's give it a try. Let's just basically cover cover the whole Caulerpa area with sand. And I mean, obviously, if all the areas that stayed buried for more than a couple of weeks, the Caulerpa was gone. So, so was the native algae, which were not many, by the way, because most of it was dominated by Caulerpa. So, I mean, this could be a tool, could be, it's very context dependent. We just did this because doing this on purpose, it would be very, very expensive. We just took advantage of, you know, all this material being dumped in the middle of the channel. So, okay, let's do this. And then João will talk about this. He will show you the numbers and the effects. Biocontrol, obviously, everybody, you know, has crossed everybody's mind, biocontrol. And we tried these two species did this simple experiment with these two species of locals of native sea urchins, because we had some reports, people that, you know, they guarantee saw them eating Caulerpa. And, you know, we had many people coming to us, no, I've seen it, I dove the other day in this place, and I'm sure they were eating Caulerpa. And you go, okay, let's test that, let's see if it's true. This is work done by Manuel Sardinha with our help. But it's also a very simple experiment. Basically, we built some cages and we put the sea urchins in there and gave them nothing to eat but Caulerpa and waited to see what happened. And the outcome, well, unfortunately for the sea urchins, well, the ones that didn't die, the Sphaerochinus granularis, so these ones, actually some amount of Caulerpa was. Yeah, this is the amount. Yeah, exactly what I'm saying. So some of the Caulerpa disappeared or was not estimated in the quadrat. So apparently a drop in the cover of Caulerpa. For this species, very neglectable. But what we realized is what these guys were doing is they might aid a little bit. We're not sure. But what was most obvious, they were basically lifting it. So they were because they couldn't go anywhere. Probably they were just lifting it. That's probably what people saw when people, you know, they were sure the sea urchins were eating the Caulerpa. So these guys that displaced it, they didn't die. They didn't die as much. Actually, these guys that displacement, they didn't die as much. The other guys that actually started eating, most of them died in the end of the experiment. So it's not good for them. I don't think they will decide to eat Caulerpa if they can have other stuff available. So not much success there either. And then some other crazy ideas, you know, that occurred when we came across with literature and papers like this that talk about the use of ultrasounds in killing single cell algae, you know, simple algae, and Caulerpa is a big cell, right? So maybe this has potential. I don't know. I'm not sure. I've never seen anything. I'm not sure if anyone has tried this. But it's been done commercially. You know, if you look into the internet, you can find all different solutions for this, for pound cleaning, ultrasonic mechanisms that kill all the single cell algae. It's been used in aquariums for, well, not in aquariums. I'm sorry. This next slide. But I don't know. It could work. I mean, if we could come up with a prototype and you could do some experiments and maybe it could be a solution. There's obviously some problems, some issues with this, especially here where you have so many cetaceans around and so close. I don't know if it's going to be an issue. I'm not sure if the frequencies and the intensity that would be needed would affect marine mammals or not. I mean, we would have to try, we'd have to test. And hopefully the good thing about this, if it worked, hopefully, if it's species specific, meaning that if it just disrupts the structure of the single cell algae and doesn't really harm the native algae, that would be perfect. That would be really interesting. And this is, you know, it would be low cost because basically you need to just power this transducer that would be pointing to the area or whatever where you need to kill the algae, and you don't have to use chemicals. You don't have to use, you know, potentially low impact. I don't know. It's just an idea. I would like to pursue this further, but for now, this is just an idea. Other ideas also come when you come across with things in the literature, like when you start thinking about, oh, of course, and then you also think about, okay, this is also used in cleaning aquarium and cleaning ponds. So maybe we could, scale up something like this, and maybe if we can flash the right intensity, the right frequency, the right amount of UV light in the Caulerpa beds, then maybe it would, I don't know, could have an effect. We haven't tested it yet. We can test this in a very simple, just buy one of these flashlights and just run some simple tests and see what happens. But again, just another crazy idea. Might work, might have potential. We don't know. And then some other methods might be very effective, but maybe not so consensual. So I don't think this will be very useful. Thank you all for your attention.